Hello, ladies and gentlemen. So today what I want to do here is I want to graph this cosine function, okay? So um, we're going to again use the systematic technique, and what we're going to do is we're going to start by finding the period, okay? Now again, for the sine, the cosine, the secant, and the cosecant, the period is 2 pi over b, where if we look at this piece, it would be the cosine of bx plus c, just to give us a consistent language about what these numbers inside are. In this case, you can see that your b is 3, so your period is 2 pi over 3. Okay. Remember that the period um, is the portion of the graph that repeats, the repeating piece. Okay. Okay. We're then going to have the increment. Okay. The increment is the spacing between the landmarks of the curve. And for us, it'll be period divided by 4, which in this case will be 2 pi over 3 divided by 4. Okay? Let's figure out what that is. So if I take 2 pi over 3 and I divide it by 4, then I don't know how to divide it by a whole number like that. So what I can always do is I can say it's 2 pi over 3 divided by the fraction 4 over 1. Because of course we know that the fraction 4 over 1 is the same as the number, the whole number 4. But now we know how to handle this because whenever we divide by fraction, we multiply by the reciprocal. So this becomes 2 pi over 3 times reciprocal of 4 over 1, which is 1/4. 2 pi times 1 is 2 pi, and 3 times 4 is 12. I can divide the top by 2 and the bottom by 2 to give me, in this case, pi over 6. Okay, so my increment is just pi over 6. And now the final thing we need to do to be able to graph this trigonometric function is to find our starting point. Now our starting point is going to be given by setting the inside of the cosine expression equal to 0. In this case, 3x minus 8 pi. So let's erase this and let's find out what the starting point is. Okay. So if I set this equal to 0, I'm going to get 3x minus 8 pi equal to 0. So for this, we want to get the x by itself. We want to find out what x is. So I'm going to add 8 pi to both sides. So plus 8 pi plus 8 pi. That's going to leave me with 3x on the left and 8 pi on the right. Then we have 3 next to x, which means 3 times x. What's the opposite of multiplication? The opposite of multiplication is division. So I divide both sides by 3. 8 thirds, 5. Okay. So our starting point will be 8 pi over 3. Okay. So now, with this setup, we're now prepared to graph this trigonometric function. Okay. Now let me remind you about the landmarks of the cosine. Okay. If I just take a normal cosine, the parent function, then the parent function looks like this. And we know that the parent function is 0, pi over 2, pi, 3 pi over 2, and then 2 pi. and it goes down to -1 in the y here, and 1 here. This is the parent function, the cosine of x. Okay? And remember, the point of the starting point, or our point in the starting point, is that it tells us the corresponding x value for this function, where this is on the parent function. Okay? With the one caveat. In this case, since the coefficient of the cosine term, negative in this case, is negative, instead of being 1 here, for this one, it'll be -1. Okay? So that means that this value, instead of being 1, will be -1. In other words, we're going to imagine that it goes the opposite way. Okay? Okay, so let's begin. The first thing I want to do before I graph the thing is I want to figure out what y's we're going to have. The x's we already know. A power 3 is our starting point. If cosine takes on the value -1, then this will be -1 times -2, which is +2. 2 minus 2 is 0. Okay, we need to have the y value 0. Now, if cosine takes the value 1, 1 times -2 is -2. -2 minus 2 is -4. So we need to have those values. So what I want you to notice there is that I'm going to draw my graph paper with the x-axis up here and with a lot of y down here. Yeah. One thing, and I'm doing that because I'm choosing to draw it in such a way that the graph will come out, let's say, pretty, let's say, or nice looking. So now I'm gonna write out this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 2, 3. Let's label these. So these are by pi over 3. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Okay. Hang on. I know what I'm going to do. Yeah. Yeah. 1, 2, 3, 4, 5, 6, 7, 8. This will be 8 pi over 3. This will be 9 pi over 3. Well, okay, I'll worry about that in a moment. I'm going to show you something cool about this. Okay. So basically, check this out. The 8 pi over 3 is our starting point, but I want you to remember, we need to add the increment to find out our important points. So we're going to make the starting point in terms of pi over 6 so that it'll be easy to add the increment the 4 times. So I multiply the top and bottom by 2. This is 16 pi over 6. Okay? So then the main points will be 8 pi over 3, which we can see here is 16 pi over 6 here. And if you guys noticed, we know that pi over 6 just happens to be half of pi over 3. So I just split these gaps, which were our original ones, into halves at least over here. So in other words, these are still by pi over 3. Anyway, so this one is going to be 17 pi over 3. This one is going to be 18 pi over 3, which if you 18 pi over 6, which of course is still 9 pi over 3. So I'm going to put that here, but I'll just label it like this. 18 pi over 3. Then this one is 19 pi over 3. And then this one is 20 pi over 3. I'm sorry, 20 pi over 6. These are all by 6s. 6, 6, 6, and 6, yeah. So I added 1, 2, 3, 4 times. Right? So this should be one period of the function. Okay? And now I'm gonna graph the points. Now remember, because of the choice of starting point, we know that the pattern of the curve will follow that of the parent. With the only exception is that in this case, since it's negative, instead of starting from the top, we're going to start from the bottom. So we know that at 8 pi over 3, because of the calculations we did earlier, our discussion, we know that it'll start here at the bottom, which will be -4. One increment over, we're going to get our landmark, which is where it's at 0. In this case, when cosine is 0, right, 0 times -2 is 0. So then it'll end up being 0 minus 2, which is -2. It'll be right here, I believe, yeah. Then, when we move one increment to the right, because it's negative, instead of being at the bottom, it'll be at the top, right? So that'll be here. And then, at our next increment, it'll be here again, because it'll be back at the 0, and then our next increment will be back at the starting point, which is here, because it's one period. So now here it's going to be rough. Oh wow, I actually, looks like I pulled it out. Very nice. Okay. And of course, in this part, these thirds are sliced into sixes, so I can do another period right here real quick. Like this. Like that. Okay. Okay. So there we have it. We graphed this function. Now, as I may have mentioned in a different example, since this starting point is let me see here, is 4 times, well, it's 4 times the period. At the very least, it's bigger than the period. That means I can subtract the period if I want to find a more convenient, let's say, x value as our starting point. Because remember, the period is one portion of the graph that repeats. So for example, in this case, I can see one period is like this. That's one period. There's another period here of the graph because that's a repeating portion. And so therefore, if I subtract a period, I can get a portion of the graph where if I subtract a period, I can get another place where I can apply my technique of knowing the pattern of the graph from the parent. Okay. Okay. Let me also make a different point here. In this example, I think you'll notice I indicated a period to be indicated by this distance because this is the repeating part, or by this distance because this is the repeating part, just as this distance is the repeating part of the parent function, right? The 2 pi is the period of the cosine, right? I do want to make a brief aside that's not important for this problem, but I want to remind you that in general, what the period is any part of the graph that repeats. So because this graph repeats forever like this is of course the period we're interested in because it's easy to graph. But if I were to move it any which way like this, I will arrive at a piece of the graph that repeats. As long as this distance is the same and I slide it this way, I'll get a piece of the graph that repeats. Okay, like let's say here, let me see here. So let's say I take this distance and I move it here. Then I get this piece. Well, in my graph, it's kind of messed up. It should actually be over here, right? Yeah. Well, these separations are not perfect because I drew them by hand and stuff like that. But I think you guys see what I'm saying. Yeah, you can see that here, this is shorter than that one. So of course, it's not going to line up perfectly. But in the real case, in our minds, in the ideal of this cosine graph, we know that if we were to take that period distance and we slide it and we look at the points in the graph, we'll get another repeating portion. Okay? Okay. Now let's look at what we were saying earlier. We drew it here. We used our starting point. We added our increment 4 times to find the major location of the landmarks, right? And then we graphed them with the caveat that since it was negative in front of the cosine, instead of following the parent, it'll just be the parent flipped over. If it is in positive, then we would have just followed the parent exactly. Okay. The one thing I want to do here is So again, in this case, we said, okay, starting point is 8 pi over 3, which is 16 pi over 6, but 2 pi over 3 is our period. So if we were to subtract 2 pi over 3 from here, we would have a starting point that would behave the way we wanted to. So if we subtract 2 pi over 3 from 8 pi over 3, we get 6 pi over 3. We can subtract again 4 pi over 3. We can subtract again 2 pi over 3. Coincidentally, we can subtract again and we get 0. So in fact, in this case, by subtracting, we can actually get an alternate starting point of 6 pi over 3, 4 pi over 3, 2 pi over 3, or 0. For me, I like 0 a lot. It'll be very easy for us to work with. Okay? And now if we use that instead, then I can add my increment very easily. This will be pi over 6. This will be pi over 6. This will be 3 pi over 6. 4 pi over 6. I just added the increment 4 times. And then again, we're going to follow the pattern of the parent function, again with the caveat that it's flipped over because the coefficient of the cosine is negative. So we're going to start at the bottom at 0. We're going to be in the middle at our first point. We're going to be at the top at our third point, the middle at our fourth point, and the bottom once again at our fifth point. And then we just combine these with a gentle curve. Okay. First, in this case, we're looking at these um, uh, tick marks as being by pi over 6 because I labeled them that way in this case. So now we can just redo, we can follow that pattern again here. The next one it'll be at the middle. The next one it'll be at the top, in the middle, in the bottom again. So we get a second period of the graph like this. Remember, we can keep adding the increment, so 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, to find the x coordinates that correspond to the particular y coordinates of this graph. Okay. So, for example, this would be 7 pi over 6 here. A skeptic among you might say, well, David, how can I trust that the point 7 pi over 6 negative 2 is on the graph? Well, let's find out. Let's plug in. You can always do this as a sanity check. Negative 2 cosine of 3 times 7 pi over 6 minus 8 pi minus 2. So I'm going to simplify this inside first. You can see that this 3 and this 6, one of them will cancel, and that'll become 7 pi over 2 minus 8 pi. Notice I just simplified this part in the middle a little bit, right? The 3 divided by the 6 is the same as 1 over 2. So 1 times 7 will be the 7, and the 2 on the bottom. Now, I ask myself, what divided by 2 is 8? 16. So I can rewrite this as 7 pi over 2 minus 16 pi over 2. You guys with me on that? Now, if you do 7 minus 16, you get negative 9. Okay? So negative 9 pi over 2. Okay? So we can rewrite this as negative 2 cosine negative 9 pi over 2 minus 2. Now, we can say, if we want, that this is just cosine of positive 9 pi over 2. If we know the even odd identities, that is to say, the cosine of negative theta equals to cosine of theta. And alternatively, just for completeness, we know that the sine of negative theta would be negative sine theta. Okay? So in this particular case, we could simply say that that's negative 2 cosine of 9 pi 2 minus 2. Okay? Now you might say, well, David, what if I don't know the even odd identities? How else could I have discovered this? Or how else could I evaluate this? Because we're about to evaluate this, right? So let me show you. We're going to draw our unit circle. Okay, I actually achieved a miracle. This is a perfect circle. No other circle has been drawn so perfect since the beginning of the universe. No, I'm just kidding. Okay, so there's 0, pi over 2, 3 pi over 2, and pi. Of course, there's a 2 pi over here, right? Let's pretend I want to evaluate this one. Okay, oops, that is not going to go well. Okay. So let's just pretend for a moment that I don't know the even odd identities, and I want to evaluate the cosine at negative 9 pi over 2 like this. So to go negative angles, instead of going counterclockwise, we go clockwise. So negative 1 pi over 2, negative 2 pi over 2, sorry, negative 1 pi over 2, negative 2 pi over 2, negative 3 pi over 2, negative 4 pi over 2, negative 5, 6, 7, 8, 9 pi over 2, negative. So that's located here. The x value there is 0. And of course, the x value of the terminal side of an angle is the cosine of that angle. So we would know that this is 0, the cosine term anyway. If we want to do it, if we know our even odd identity, we would do cosine of 9 pi over 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9 pi over 2. So the terminal side associated with 9 pi over 2 is not the same as the terminal side associated with negative 9 pi over 2, but their cosine is the same. But so in any case, this is 0. 0 times negative 2 is 0. Minus 2 gives us negative 2. So we can in fact verify that at this x value, 7 pi over 6, we do in fact get negative 2 as our value. So we know for a fact that this is actually the value of the point that is there. Okay, let me just clean this up a little bit here. Okay, that last erasure was bad. We'll just put it in real quick. So just to recap, what we did was we found the period of our given trigonometric function graph. We found our increment by dividing our period by 4 and simplifying. We then found our starting point by setting the inside of our trigonometric function equal to 0. We then made the increment and the starting point have the same denominator, so it would be easy to add them. And then we graphed the function knowing that if we use that starting point and if we use that increment, we will hit the landmarks of the parent. With the caveat that since it was negative here, instead of going down and up like this for the cosine, we would go down, up, down, because it's negative here, okay? And then we observed, well, that original starting point we got, 8 pi over 3, it was big. And by big, we don't mean that that's a bad thing necessarily in this case, but when you want to draw a graph, maybe you just want to see the values like in a normal graph paper that doesn't extend off the side of your page. So what we saw is that we could respectively subtract or add the period to the starting point to get a more convenient starting point. And again, remember, if you were solving an actual problem where you actually had to do this, you might actually have an actual like range of values for x that might be interesting to you for your problem. And so in that case, we could do the same thing, and we would just add or subtract the period to the starting point until you find the region of the graph where you're interested in. And then from there, you just graph it by taking that alternate starting point and adding the increment the 4 times as is necessary to find the location of the landmarks. And so in this case, we did that by realizing that if we took 8 pi over 3 and we subtracted the period 4 times, we actually find the beautiful alternate starting point of 0, which of course is very nice. Because then 0, and then plus the increment pi over 6, plus the increment pi over 6. Again, plus the increment pi over 6. And then plus the increment of pi over 6. And we just follow the pattern of the cosine. In this case, as we mentioned before, because this was negative, flipped over. If this had been a positive, it would have followed the normal pattern of starting at the top and going like that. I hope you've enjoyed this example, and thank you so much.